Right, so for our different geometric proofs that we're going to use, we're going to now talk about, we have, two definitions and then one theorem to go through. And then we are going to go through an example or two. I'm going to kind of look at the homework and see where we're at with that. All right, so our first thing that we're going to talk about is a definition. So these are things that we're going to use underneath the reasons column when we do proofs. Okay, we might be using these things. So the first one is definition of congruent. Now this might feel weird because we defined congruent as, what does congruent mean? Equal or the same. But when we're dealing with a congruent symbol, we can't just switch over to an equal symbol without using this definition. It's kind of weird because in our brains, we know that that congruent symbol really just means equal, but I don't know, we have to state it. We have to do all the little itty parts. So we have two things that can be congruent right now. We have segments that can be congruent. So we would say definition of congruent segments, which tells us if two segments are congruent, then we know that they're equal lengths. Their lengths are equal. Okay, so that would look like if I knew segment EF. When we do congruent, we do call it segment EF with a name. So we put that little line above. So segment EF is congruent to segment, MN. So if we're given that, what we can switch it to is, instead of saying segment EF is congruent to segment MN, we can just say EF, and for that distance, we get rid of the segment sign. We say from E to F. And we're going to switch it to an equal sign. Equals. And then instead of a segment MN, we just say from M to N, that distance, that length. Okay, again, it feels a little silly because, one, this is what I taught you what it means, because it's the definition. But we do have to, in a proof, we have to explain every little step. It's almost like we're explaining it to like a 2-year-old. Like every little thing, you have to say what it is and you have to explain it. And then they're going to say, why? And you have to say, because of this. And then they're going to say, why? And you keep going and going. Okay? We also have definition of congruent angles. So we have segments and angles. All right, and we know that two congruent angles means that they're going to have, their measures are going to be equal. They have equal measures. And really, today we're not talking necessarily about that definition, but just how we show it, because we're going to have to show it in our statements. Okay, And what that looks like when you do two congruent angles, we would say like angle 3 is congruent to angle 4. But then when we go to that measure, when we do a measure, this time we put the little m in front. And that's actually saying how many degrees angle 3 is equal to the measure, or how many degrees angle 4 is. Now I put arrows both ways because it can go both directions. If we know that they're equal, then that means that they are congruent. So it's not always we're working congruent to equal. Sometimes we're working from equal to congruent. All right, we have one more theorem that we're going to talk about today, and then we are going to just do one example. Okay, we have our midpoint theorem. Okay, so remember with a midpoint, if I have TW, it's a segment, and I want B to be the midpoint, where is B going to go for the midpoint? In the middle. Okay, so we know B is the midpoint. Of segment TW. And since B is exactly in the middle, what do we know about those two parts? They're equal. But that's our definition. Our theorem is going to say that they're congruent. So we're going to say TB, segment TB, is congruent to segment BW. So this is the theorem. Or we can jump to saying TB equals BW, but that would be our definition. So kind of depending on what we're working with, sometimes we're going to use our theorem if we're just working in congruent symbols. We'll use our midpoint theorem, saying TB is congruent to BW. Or if we need to work with equations, we might just jump straight to TB equals BW. All right, we have one example that we're going to do. I'm trying to figure out if we're going to have enough lines. You need 1, 2, 3, 4, 5, 6, 7, 8-ish lines after we write it. Should have enough room. All right, so here's our example. If you want to draw like a line across saying that that is the work that we just did. Now we're going to move on to our example. Okay, so for our example, we're going to have a segment, H to K. J is going to be our midpoint. Yep, this is the example. Okay, we know HJ is x plus 4. And JK is 15. Yesterday we talked a little bit about if-then statements. The if part is the given. The then part is the conclusion. Another way that proofs can be set up is they can tell you a given, and they just write out given. Okay, what we're given, I said it, but there's not really a good way to write it, is we know that J is the midpoint of HK. I'm not writing it all out because, I don't know, this is a lot to write. We get the idea. J is the midpoint of HK. And what we need to prove, what it's asking us to end with, is x equals 11. All right, so let's think through this a little bit, kind of come up with our game plan before we go into it. How are we going to prove that x is 11 if we know j is the midpoint? What? Okay, how do we know 15 minus 4? Okay, that's one way to do it. We could say h to k is 30, but what do we know about a midpoint? It's the middle, so h to j is the same as j to k. So we're going to say this is the same as this. So what plus 4 is 15? 11, right? Makes sense? Okay, we've already done this problem. That was what we reviewed on e-learning days, that you guys wrote a problem like this and solved it. We just have to show it in a proof now. So with a proof, remember it's a 2-column proof. Okay, on the left side, we're going to learn 2 other ways of doing proofs called flow proofs and paragraph proofs, but we'll wait until chapter 4 to do those. We're going to just learn one way to do it right away. On the left side, we have statements. And what question does statements answer? The what? And what goes on our other side? Our reason, which might answer the question why, or it might even answer the question how. All right, so for our first statement, we're going to state what we were given. So what information did this problem tell us? Yeah, it tells us that j to k is 15. That one they didn't even say in the given over here, but it was part of the picture, so they did give us that information. jk equals 15. What else are we given? Yep, it gives us that. I already started writing a different one. I'm so sorry. Hj is equal to... Nope. What part is given to us? Hj is x plus 4. Okay, those are from the picture. And then from the actual, given here, we know j is the midpoint of HK. Okay, so all of this, all 3 of those are the given. So our given is always what we're given, either in words, or it can be what they told us in the picture, and we just have to name what we are given in that picture. All right, so number 2. If I know that j is the midpoint of HK, what did that tell us? Yeah, both sides are equal. So we know now, because j is the midpoint, I'm going to do a little arrow here for my thinking. We know HJ is equal to JK. Now, we went with the equals. So is that going to be the midpoint theorem or the midpoint definition? The definition. And so we're going to write definition of a midpoint. I'm just going to write def for definition of midpoint. If we had used a congruent symbol, then it would be the midpoint theorem, but we just went straight with equals, and that's fine. Okay, step 3. I'm going to skip a line here so I can do a little bit of some arrows. HJ, what did we say HJ is the same as? We said it was x plus 4. So I'm switching it out for something it's equal to. And instead of saying JK, what did we know JK was the same as? 15. So what do we call that? It's from that 2 times ago when we did that glue in. When we switch something out for its equal value. Substitution. Good, so that's our substitution property of equality. Okay, now we have to always remember what we're trying to prove. What we're trying to prove is that x is equal to 11 by itself. So in step 4 here, some people can do this in their heads, and they know right away just x equals 11. If I know x plus 4 is 15, then x equals 11. They might skip this step that they're showing their work. What did they really do to both sides to get x equals 11? They minus 4. If you minus 4 on one side, you minus 4 on the other side. Now, when you do your practice today, the practice does skip this work. It's going to go straight to the answer, and you have to think, how did they get from this one to this one? Well, they got rid of the plus 4, and what do we have to do to both sides to get rid of plus 4? So is that addition property of equality or subtraction property? Subtraction. Because they subtracted on both sides. How are we feeling? Tired? Me too, man. Okay, hopefully this is starting to make